So get your new notes out. This is 4.4b, the second fundamental theorem of calculus. Yes, there's two of them. Second fundamental theorem of calculus. Your second fundamental theorem of calculus. Let's talk about this other one. And this is often called the accumulation. The integral is an accumulation, right? So before, just to recall, when I said derivative, you said slope, right? A derivative is slope. An integral is an accumulation. Derivative tells you a slope, and an integral tells you an accumulation. Accumulation. How much you have like gathered together over a period of time, right? If you start from A to B, you have some amount that you have gathered when you started at A and you ended at B. Like, you know, if you say a squirrel has a rate of gathering nuts, it gathers like three nuts every minute. 3 acorns per minute is what its rate of gathering is. Well, how can you figure out how many acorns it's gathered over an hour? Well, you would integrate the function 3x, 3 acorns every minute. X is in minutes. You accumulate how many acorns you are gathering in that time. The same thing happens with any other function that you have a rate of. You're integrating a rate, you get an amount. You're getting an accumulation. So the second fundamental theorem of calculus uses this accumulation idea, this idea of accumulation, and it creates an accumulation function. Accumulation function is the second fundamental theorem. Second fundamental theorem is called the accumulation function. And it says it's f of x equals the integral from some number to x of an equation, usually relating not x, but t, dt. This is the second fundamental theorem of calculus. And so what it's saying is, A is just any constant number, any constant. X is the, like where we're going to end. This is our variable. And f of t, t is usually time, but this is a function of time. A function of usually time. And so what we're saying is this f function, this capital F function here, is the equation that describes how much we accumulate from some starting value to a variable. And so this is a variable accumulation. Let me give you a picture here. Oops, let me give you a picture here. It'll maybe help make a little more sense. So if I have a function f of t is, let's say, what's a good example that I give here? Let's say it's negative x squared plus 5. Negative t squared plus 5. Negative t squared plus 5. So if I have a graph of this equation, right? If I have a graph here, 1, 2, 3, 4, 5. My graph looks something like, something like this, right? This is f of t, right? Up to 5, it's a parabola, right? We have this parabolic curve, curving like this, right? So if I want to say, tell me the amount accumulated, let me say that f of x is the integral from 0 to x of this equation. What does this function look like in terms of this equation? What does this function look like? This capital F accumulation function. What does the accumulation function look like? Well, if I start at 0, if I say, okay, what is capital F of 0 equal? What if I plug 0 into this accumulation function? How much have I accumulated so far? How much have I accumulated so far? I've finding area, right? The area from 0 to some number. I'm looking for the area from 0 to some number. Area of, well, here I'm looking for the area from 0 to 0. Well, that starts at 0 and ends at 0, right? That's this area here, which is 0. Right? The accumulation, it doesn't accumulate anything. So we're starting off on 0. But now let's say if I do the accumulation, let's do another one here. Draw this graph again. And now let's say 1, 2, 3, 4, 5. Again, my curve looks something like this. What does f of 1 look like? F of 1 says, well, I'm starting here at 0. I'm starting at 0. And I'm going to 1. I have accumulated this amount of material so far. So I've done the integral from 0 to 1 of f of t, right? Which is some number, some positive value, right? This is maybe like, I'll call this, well, we could calculate it, right? We could do the calculation of this. We could do the integral. So cubed, 1/3, 1, plus 5. Let's call this 1/3. Okay. So I've gained 1/3. I've accumulated 1/3 of a value, 1/3 of an amount, right? Let's keep going. Let me, again, give another value for f. 1, 2, 3, 4, 5. If I do it again, let's say I want f of capital F of 2. That's the integral from 0 to 2 of f of t, right? So now I have accumulated this amount. I've increased my amount of accumulation. I've gained more. I've increased my amount. Now it's maybe like, I don't know, 1.8 or something. Or maybe it's like, maybe let's go 1 2/3. Something like that, right? It's increased. I've gained my amounts, right? I've increased my amount. If we kept going all the way to 4, we would show that we increase more and more, right? We're gaining more, we're accumulating a higher amount of stuff. Okay? We started with 0. We're accumulating a higher amount of stuff. So my f value is getting bigger and bigger as we go along. As x increases, the value of the capital F function increases, so long as my integral part is positive. I'm gaining more, right? I'm gaining more, right? I'm accumulating more, accumulating more. I had nothing here. I was accumulating nothing because I started at 0. And then I gained a little bit when I went to 1, when f of 1. I gained a little bit more when I'm at f of 2. I get a bigger amount. 3, 4, 5, we can keep going, right? We'll get bigger and bigger amounts. So my accumulation function is increasing. And it's only increasing because my graph up here is positive. If this graph was my graph of f, lowercase f, is positive. It's a positive graph, so I'm gaining more. So if we were to try to graph capital F of x, what would that look like? Right? If we try to graph capital F of x, well, at 0, it's 0. We had nothing accumulated. Right? And then we had 1/3. At 1, it's 1/3 accumulated. So 1, 2, 3, 1/3, maybe like here, right? 0 to 1/3. And then we had 0, 1/3, and we were maybe slowing down the accumulation. Though we didn't gain as much. If you look at it here, between 0 to 1 and 1 to 2, this amount gained is more than this amount gained, right? If you look at it, this amount gained here is more gained compared to this section here is less gained. Right? Does that make sense? If we cut it at 1, between 0 and 1 and 1 to 2. In the section from 0 to 1, I have this is like a bigger area, right? Because it's taller graph, the bigger area, and between 1 to 2, there is less that I've gained. Right? There's less that I've gained between 1 to 2. So it's like here, whoopsies, like here, I gained a little bit, and then I gained a little bit more. So I gained a lot, I gained like a lot, and then a little, lot, oopsies. I gained quickly, and then I slowed down how much I was gaining, right? Gained quickly, and then slowed down how much I was gaining. So the graph would look something like this, perhaps. My graph of capital F of x. Graph of capital F of x would look something like this, right? Gained a small amount, decreasing amounts that I've gained. I gained more and then less and less and less. So I went up really fast and then slowed down, slowed down, slowed down. Right? And we can find this by using the integral equation, right? So this is going to be negative 1/3 t cubed plus 5t evaluated at 0. That's equal to 0. And this is again 1/3 t plus 5. T is going to be, maybe not 1/3, some other amount. 1/3 plus 5, 5/3, 5 1/3. 5 1/3. Would be 4 2/3. And then maybe this is 6 1/3. Anyway, the key idea here is that you gain a large amount, then you gain less, and gain less, and gain less, and your amount that you increase has dropped off. In fact, it's going to look something like, let me show you here. It's going to go up, and then it's going to peak 3, 4, right here at 4, and then it's going to start going down. and it's going to start going down again. Because here, at this point right here, this is where I start accumulating, I stop growing, right? My graph of f stops growing and starts shrinking. Right here at 4. 1, 2, 3, 4, right? Because I have stopped gaining ground. I've stopped adding to my area. When I hit the 0 here, I've stopped gaining my area. And now if I go below here, if I keep going down here, I'm now losing area. All this area down here, this is going to be subtracted. So my graph is going to have to go down. My amount I've accumulated has shrunk because the graph is negative. I'm losing an amount. I'm losing amounts of stuff, right? I'm losing, this f is how much I have gained, right? I'm gaining stuff from 0 here until 4. I'm gaining things. I'm adding to my total. I'm gaining less and less and less, but I'm still gaining. I'm gaining amounts. I'm gaining less and less and less until this value right here at 4, and then I start to lose some of my stuff. I start to lose the stuff until some point that I start to have less stuff. I start to have negative stuff. I've lost more than I've gained. I've gained more than I've lost, and now I'm losing some, and now I've lost more than I've gained. So I'm gaining an amount here. When it crosses this line, I'm starting to lose amounts like this. So I'm losing amounts down here until I lose more than I've gained down here. And if I graphed this out all the way, right, this would be some parabola, right, that would look like this. My function here would look something like this, which is a x cubed equation, a cubic equation. In fact, this would look like negative 1/3 x cubed plus 5x is what this would look like. And so when you do this accumulation function, what you are getting is the antiderivative. When you do the accumulation function, what you are getting is the antiderivative. I realized we were out of time. I did not even know. Okay, so here's what I want you to do. Try some of these accumulation functions. I would like you to do 2 questions on this handout here. I wanted you to do, where to go? 67 and 68. 2 questions here. Page 293, 67, and 68. That's your assignment. Doing this idea of accumulating, right? Finding this accumulation function, finding the graph, trying to determine where things are growing and shrinking. 67, 68, those 2 questions in the homework. We will go over this, well, tomorrow. I'll see you all tomorrow, so we'll go over this again then. All right, everybody. Good job today. Thank you very much. I will see you all next time. Well, tomorrow. Say goodbye in the chat. Once you say goodbye, you're free to go.